8.22 The fourth generation Intel registered sine Core TM processor family, 2013. The fourth generation Intel Core processor family spans Intel Core i7, i5, and i3 processors based on the Haswell microarchitecture. Intel Xeon processor E3-1200V3 product family is also based on the Haswell microarchitecture. 2.2 More on specific advances. The following sections provide more information on major innovations. 2.2.1 P6 family microarchitecture. The Pentium Pro processor introduced a new microarchitecture commonly referred to as P6 processor microarchitecture. The P6 processor microarchitecture was later enhanced with an on-die level 2 cache, called Advanced Transfer Cache. The microarchitecture is a three-way superscalar, pipelined architecture. Three-way superscalar means that by using parallel processing techniques, the processor is able on average to decode, dispatch, and complete execution of, retire, 3 instructions per clock cycle. To handle this level of instruction throughput, the P6 processor family uses a decoupled, 12-stage super pipeline that supports out-of-order instruction execution. Figure 2:1 shows a conceptual view of the P6 processor microarchitecture pipeline with the Advanced Transfer Cache enhancement. Figure 2:1, the P6 processor microarchitecture with Advanced Transfer Cache enhancement. To ensure a steady supply of instructions and data for the instruction execution pipeline, the P6 processor microarchitecture incorporates 2 cache levels. The level 1 cache provides an 8K byte instruction cache and an 8K byte data cache, both closely coupled to the pipeline. The level 2 cache provides 256K byte, 512K byte, or 1M byte static RAM that is coupled to the core processor through a full clock speed 64-bit cache bus. The centerpiece of the P6 processor microarchitecture is an out-of-order execution mechanism called dynamic execution. Dynamic execution incorporates 3 data processing concepts: Intel registered sine 64 and IA32 architectures, system bus, frequently used, less frequently used, bus unit, second-level cache on-die 8-way, first-level cache 4-way low latency, front-end, fetch decode, execution instruction cache microcode ROM, execution out-of-order core, retirement, branch history update, BTS's branch prediction, OM 16520, Volume 1 2-7, Intel registered sine 64 and IA32 architectures, deep branch prediction allows the processor to decode instructions beyond branches to keep the instruction pipeline full. The P6 processor family implements highly optimized branch prediction algorithms to predict the direction of the instruction. Dynamic data flow analysis requires real-time analysis of the flow of data through the processor to determine dependencies and to detect opportunities for out-of-order instruction execution. The out-of-order execution core can monitor many instructions and execute these instructions in the order that best optimizes the use of the processor's multiple execution units, while maintaining the data integrity. Speculative execution refers to the processor's ability to execute instructions that lie beyond a conditional branch that has not yet been resolved, and ultimately to commit the results in the order of the original instruction stream. To make speculative execution possible, the P6 processor microarchitecture decouples the dispatch and execution of instructions from the commitment of results. The processor's out-of-order execution core uses dataflow analysis to execute all available instructions in the instruction pool and store the results in temporary registers. The retirement unit then linearly searches the instruction pool for completed instructions that no longer have data dependencies with other instructions or unresolved branch predictions. When completed instructions are found, the retirement unit commits the results of these instructions to memory and/or the IA32 registers, the processor's 8 general-purpose registers and 8 x87 FPU data registers, in the order they were original, issued, and retires the instructions from the instruction pool. 2.2.2 Intel Net Burst Registered Sine Microarchitecture. The Intel Net Burst microarchitecture provides, the rapid execution engine. Arithmetic logic units, ALUs, run at twice the processor frequency. Basic integer operations can dispatch in 1/2 processor clock tick. Hyper pipeline technology. Deep pipeline to enable industry-leading clock rates for desktop PCs and servers. frequency headroom and scalability to continue leadership into the future, advanced dynamic execution, deep out-of-order, speculative execution engine, up to 126 instructions in flight, up to 48 loads and 24 stores in pipeline 1, enhanced branch prediction capability, reduces the misprediction penalty associated with deeper pipelines, advanced branch prediction algorithm, 4K entry branch target array, new cache subsystem, first level caches, advanced execution trace cache stores decoded instructions, execution trace cache removes decoder latency from main execution loops, execution trace cache integrates path of program execution flow into a single line, low latency data cache, second level cache, full speed, unified 8-way level 2 on-die advanced transfer cache, bandwidth and performance increases with processor frequency. 1. Intel 64 and IA32 processors based on the Intel Net Burst microarchitecture at 90 nm process can handle more than 24 stores in flight. 2 to 8 Volume 1, high performance quad pumped bus interface to the Intel Net Burst microarchitecture system bus. Supports quad pumped, scalable bus clock to achieve up to 4x effective speed. Capable of delivering up to 8.5 GB of bandwidth per second. Superscalar issue to enable parallelism. Expanded hardware registers with renaming to avoid register namespace limitations. 64-byte cache line size, transfers data up to 2 lines per sector. Figure 2-2 is an overview of the Intel Net Burst microarchitecture. This microarchitecture pipeline is made up of 3 sections. 1. The front-end pipeline, 2. The out-of-order execution core, and 3. The retirement unit. Figure 2-2 the Intel Net Burst registered sign microarchitecture 2.2.2.1 The front-end pipeline. The front-end supplies instructions in program order to the out-of-order execution core. It performs a number of functions. Prefetches instructions that are likely to be executed. Fetches instructions that have not already been prefetched. Decodes instructions in micro operations, generates microcode for complex instructions and special purpose code, delivers decoded instructions from the execution trace cache, predicts branches using highly advanced algorithm. The pipeline is designed to address common problems in high-speed pipeline microprocessors. 2 of these problems contribute to major sources of delays, time to decode instructions fetched from the target. Intel registered Science 64 and IA32 architectures. System bus, frequently used paths, less frequently used paths. Bus unit, third level cache optional. First level cache 4-way, second level cache 8-way. Front end, fetch decode, trace cache microcode ROM. Retirement, BTB's branch prediction, execution out of order core, branch history update, OM 16521. Volume 1 2-9, Intel registered Science 64 and IA32 architectures. Wasted decode bandwidth due to branches or branch target in the middle of cache lines. The operation of the pipeline's trace cache addresses these issues. Instructions are constantly being etched and decoded by the translation engine, part of the fetch decode logic, and built into sequences of micro-ops called traces. At any time, multiple traces, representing prefetched branches, are being stored in the trace cache. The trace cache is searched for the instruction that follows the active branch. If the instruction also appears as the first instruction in a prefetched branch, the fetch and decode of instructions from the memory hierarchy ceases, and the prefetched branch becomes the new source of instruction. See Figure 2-2. The trace cache and the translation engine have cooperating branch prediction hardware. Branch targets are predicted based on their linear addresses using branch target buffers, BTBs, and fetched as soon as possible. 2.2.2.2 Out-of-order execution core. The out-of-order execution core's ability to execute instructions out of order is a key factor in enabling parallelism. This feature enables the processor to reorder instructions so that if one micro-op is delayed, other micro-ops may proceed around it. The processor employs several buffers to smooth the flow of micro-ops. The core is designed to facilitate parallel execution. It can dispatch up to 6 micro-ops per cycle. This exceeds trace cache and retirement micro-op bandwidth. Most pipelines can start executing a new micro-op every cycle, so several instructions can be in flight at a time for each pipeline. A number of arithmetic logical units. ALU instructions can start at 2 per cycle. Many floating point instructions can start once every 2 cycles. 2.2.2.3 Retirement unit. The retirement unit receives the results of the executed micro-ops from the out-of-order execution core and processes the results so that the architectural state updates according to the original program order. When a micro-op completes and writes its result, it is retired. Up to 3 micro-ops may be retired per cycle. The reorder buffer, ROB, is the unit in the processor which buffers completed micro-ops, updates the architecture state in order, and manages the ordering of exceptions. The retirement section also keeps track of branches and sends updated branch target information to the BTB. The BTB then purges prefetch traces that are no longer needed. 2.2.3 Intel Registered Sign Core TM Microarchitecture. Intel Core Microarchitecture introduces the following features that enable high performance and power-efficient performance for single-threaded as well as multi-threaded workloads. Intel Registered Sign Wide Dynamic Execution enable each processor core to fetch, dispatch, execute in high bandwidths to support retirement of up to 4 instructions per cycle. 14-stage efficient pipeline, 3 arithmetic logical units, 4 decoders to decode up to 5 instructions per cycle, macro fusion and micro fusion to improve front-end throughput, peak issue rate of dispatching up to 6 micro-ops per cycle, peak retirement bandwidth of up to 4 micro-ops per cycle, advanced branch prediction, stack pointer tracker to improve efficiency of executing function procedure entries and exits. Intel Registered Sign Advanced Smart Cache delivers higher bandwidth from the second-level cache to the core, and optimal performance and flexibility for single-threaded and multi-threaded applications. Large second-level cache up to 4 MB and 16-way associativity. Optimized for multi-core and single-threaded execution environments. 256-bit internal data path to improve bandwidth from L2 to first-level data cache. 2 to 10. Volume 1. Intel Registered Sign Smart Memory Access prefetches data from memory in response to data access patterns and reduces cache miss exposure of out-of-order execution. Hardware prefetchers to reduce effective latency of second-level cache misses. Hardware prefetchers to reduce effective latency of first-level data cache misses. Memory disambiguation to improve efficiency of speculative execution engine. Intel Registered Sign Advanced Digital Media Boost improves most 128-bit SIMD instructions with single-cycle throughput and floating-point operations. Single-cycle throughput of most 128-bit SIMD instructions. Up to 8 floating-point operations per cycle. 3 issue ports available to dispatching SIMD instructions for execution. Intel Core 2 Extreme, Intel Core 2 Duo processors, and Intel Xeon Processor 5100 series implement 2 processor cores based on the Intel Core microarchitecture. The functionality of the subsystems in each core are depicted in Figure 2 to 3. Figure 2 to 3 The Intel Registered Sign Core TM microarchitecture pipeline functionality. 2.2.3.1 The front end. The front end of Intel Core microarchitecture provides several enhancements to feed the Intel Wide Dynamic Execution Engine. Instruction Fetch Unit prefetches instructions into an instruction queue to maintain steady supply of instruction to the decode units. A decode unit can decode 4 instructions per cycle or 5 instructions per cycle with macro fusion. Macro fusion fuses common sequence of 2 instructions as one decoded instruction. Micro-ops to increase decoding throughput. Micro fusion fuses common sequence of 2 micro-ops as 1 micro-ops to improve retirement throughput. Intel Registered Sign 64 and IA32 architectures, instruction fetch, and pre-decode instruction queue decode, scheduler, microcode ROM. Rename alloc. Retirement unit, reorder buffer, shared L2 cache up to 10.7 GB per second FSP. ALU branch MMXS SEFP move. ALU FAT MMXS SE. ALU F mul MMXS SE. Load, store, L1D cache and DTLB. Volume 1 2 to 11.